Again, it's always the same scheme. Always, always, always. And we need to find ways how to apply this scheme. Now what if we have a low number sample? Yeah? Because we were relying on the binomial distribution to approach the normal distribution, which is only valid for a large n. Yeah? So if we have a small n, we cannot compute it like this. So what can we do? So there are two different possibilities. We can either do simulations or exact probabilities, and I will show you how, on an example, how we simulate. And we do it on Paul the Octopus. Some of you might recall Paul, which was an octopus in the soccer championship 2006 in Germany. It was an octopus that was an oracle who was predicting all the results of the German games in the tournament. And he had a success rate of 100% of 8 games. Okay, so that's the data. Yeah. Now, does this data provide convincing evidence that this octopus was a psychic? Yeah, that he could foretell the future? Or was it just lucky random guessing? Okay, that's the hypothesis. That's the question. So the null hypothesis is nothing is going on. That's a regular octopus, which means he has a 50% chance to guess the result. So he was guessing by grabbing some food through one of 2 possible containers that were put into his tank. So one was Germany wins and one was Germany loses, and he was always picking, I don't know. So if there's nothing going on, then P needs to be 0.5, yeah, because that's random guessing chance. Alternative hypothesis is larger than 50%. N is 8, and our result of our mean proportion of successes was 1. So 100% success chance. Yeah. So here we would have to be actually somewhat careful, because the conditions are not actually met. So we ignore this for the moment to demonstrate, because this is just so such a nice example. So I would like to set up a simulation scheme to test, and the idea is, let's do a simulation under the assumption that the null hypothesis is true. And then we compare the result of the simulation. We do the simulation many times. And then what fraction of simulations gave me the same result as what we observed? Yeah, and that's then the ratio of these is basically the chance to get this result, even though the null hypothesis is true. Okay. What I do is, okay, I need to come up with some simulation scheme. What I do is I create 8 random numbers between 0 and 1, and then I assign 0 to 0.49 to failure, so no success, and 0.5 to 1 to success, so correctly guessed. And I do it 8 times and count how many successes I have. And then I do it many times, and that looks like this. That's the simulation. Let's check here. So my simulation function is count. So I'm doing this with integer numbers, so count how many ones I get in 8 random integer numbers, divided by 8, and that's the percentage of correctly guessed gains in this run. And then I do it 1 million times, and compare and compute the mean, or the histogram of this. And that's the result here. That's the histogram of these 1 million octopussy. What's the plural of octopus in English? I don't know. Octopuses. I don't know. Okay. Octopuses. So there is a small number, 3,877 from 1 million, that got 8 successes in a row. But that's the distribution. So the chance is actually 3,877 divided by 1 million. Or that's 10 to the 6, so 3.9 times 10 to the minus 3. So 3 promille chance. Small, very small chance. What would you say? Why is the histogram so funnily looking here with these gaps? Do you have an idea? Because these things need to make you suspicious. We do it 1 million times. You would expect something smooth. Why is it looking like this? Because there are 9 possible outcomes of my simulation. 0, correctly guessed, 1 correctly guessed, 2, 3, 4, 5, 6, 7, 8. So that's 9 possible events. And I divide these numbers between I divide these 9 by 8. Is it true? Yes. So, so there is only 9 possible outcomes. 9 possible proportions are possible. 9 possible proportions are possible. Yeah, okay. 9 proportions are possible. And because of the binning I chose, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bins. Yeah, so I cannot get this result, just numerically. I cannot get this number. If we compute this analytically, we use the binomial distribution and ask what is the probability to get 8 out of 8 times the success probability times the failure probability. Yeah? So that's the probability of 1 game guessed, and that's the probability of 8 out of 8 correctly guessed. And that's basically the same number. Yeah? So 3 point something promille. Okay?